Hello everyone, I am Darshan A, Assistant Professor of Mathematics. In the previous sessions, we have learnt about divisibility, division algorithm and congruences. In this session, I am going to discuss about one of the important theorem in congruences, Fermat's little theorem. Let's get in. Fermat's little theorem. Let A be an integer and P be a prime number such that GCD of A and P is equal to 1, then A to the power of P minus 1 is congruent to 1 modulo P. To prove this, first I consider the integers. Proof. Consider the integers 1a, 2a, 3a, etc. p minus 1 into a. When I divide these integers by the prime number p, I claim that I don't get the remainder as 0. Suppose if MA is congruent to 0 modulo p, where m is an integer between 1 and p minus 1, where 1 less than equal to m less than equal to p minus 1, then by the definition of congruence, we should have p divides ma. But given that the GCD of A and P is equal to 1, since GCD of AP is 1, we should have P divides M, which is not possible because M is an integer less than P, so P cannot divide M. So this is a contradiction, which is a contradiction. MA cannot be congruent to 0 modulo P, hence MA is congruent to R modulo P, where M is between P minus 1 and 1, and the remainder also between 1 and P minus 1. Okay. Now let R1 be the remainder when 1A is divided by P, R1, where R1 is an element in the set 1, 2, 3 up to P minus 1. Similarly, when I divide 2A by P, I get the remainder R2, where R2 is an element in the same set 1, 2, 3 up to P minus 1, and so on. And when I divide P minus 1 into A, I get the remainder Rp minus 1, where Rp minus 1 is an element of the same set 1, 2, 3 etc. P minus 1. Okay. Now we shall show that all these remainders are distinct. Suppose if Ri is congruent to Rj modulo P and I not equal to j, where I and j are between P minus 1 and 1, then by this we should have Ia is congruent to Ja modulo P. So by the definition of congruence, we should have P divides A into I minus J. But since the GCD of P and A is 1, but since GCD of AP is 1, we should have P divides I minus J, which is a contradiction. This is a contradiction because I and J are less than P, so that I minus J is also less than P, which is not possible, as I not equal to J and I and J are less than P. Okay, so this is a contradiction. So we cannot have this, so all these remainders are distinct. Now if you observe these two sets, R1, R2, etc. are P minus 1, and the set 1, 2, 3 up to P minus 1. In these two sets we have P minus 1 distinct integers, and we have also shown that all the remainders belongs to this set, so that these two sets should be identical. Now when I multiply all these congruents, I get here 1 into 2 etc. P minus 1 into a P minus 1 times, so I get a power P minus 1 congruent to R1, R2 etc. are P minus 1 modulo P. When I multiply this, I get here P minus 1 factorial into a to the power of P minus 1 congruent to this product is same as this product, because the set 1, 2, 3 etc. P minus 1 is same as the set R1, R2 etc. are P minus 1. So this product is same as this product. Here we get P minus 1 factorial modulo P. Now GCD of 1 and P is 1, 2 and P is equal to 1, and so on, and hence the product of these terms, that is P minus 1 factorial, is also relatively prime to P, right? Every element here is relatively prime to P, so the product is also relatively prime to P. So when I cancel P minus 1 factorial on both the sides, I get here a power P minus 1 is congruent to 1 modulo P as required. We can deduce a corollary using Fermat's little theorem, that A be an integer, P be a prime number, then A power P is congruent to A modulo P. To prove this, I consider two different cases. Case 1, if P does not divide A. If P does not divide A, then the GCD of AP should be equal to 1. So by Fermat's little theorem, or Fermat's theorem, we have A power P minus 1 is congruent to 1 modulo P. When I multiply A on both the sides, I get here A power P congruent to A modulo P. Okay. In the case 2, if P divides A, then P divides A power P. Combining these two, we have P divides A power P minus A, that is A power P congruent to A modulo P. So we have the corollary. Now let us consider some problems. Prove that n to the power of 12 minus 1 is divisible by 7 if GCD of n and 7 is equal to 1. Solution. We know that 7 is a prime number, and given that GCD of n and 7 is equal to 1, so by Fermat's little theorem, we have n to the power of 7 minus 1 is congruent to 1 modulo 7, or n to the power of 6 is congruent to 1 modulo 7. Okay. Now, by the definition of congruence, 7 divides n power 6 minus 1. Now, using the property of divisibility, 7 divides n power 6 minus 1 into n power 6 plus 1. Now when I multiply this, I get here 7 divides n to the power of 12 minus 1. as required. Now consider one more problem. Find the remainder when 3 power 100 into 2 power 50 is divided by 5. Here I am going to use Fermat's little theorem. We know that 5 is a prime number and 5 is relatively prime to 3 and 2. Solution. First we have 5 is a prime number and GCD of 3 and 5 is equal to 1. Similarly, I know that 5 is a prime and the GCD of 2 and 5 is also equal to 1. Here I am going to use Fermat's little theorem. By Fermat's theorem, I have 3 to the power of 5 minus 1 is congruent to 1 modulo 5. Here I should get 2 to the power of 5 minus 1 is congruent to 1 modulo 5. Or 3 power 4 is congruent to 1 modulo 5. First, let us solve this and later we shall solve this. Now, if I raise the power, I should get here 100. So, I raise the power by 25 on both the side. I get 3 power 4 whole power 25 is congruent to 1 power 25 modulo 5. Or 3 power 100 is congruent to 1 modulo 5. Okay. So let us take this as 1. Here I get 2 power 4 is congruent to 1 modulo 5. To get 50 here, I am going to raise the power by 12 on both the side. I get 2 power 4 whole power 12 is congruent to 1 power 12 modulo 5, which is same as 2 power 48 congruent to 1 modulo 5. To get 2 power 50, I multiply 2 square on both the side. So I get 2 power 50 congruent to 2 square, which is 4 modulo 5. Let me take this as 2. Now when I multiply these two congruents 1 and 2, from 1 and 2 we have 3 power 100 into 2 power 50 is congruent to 1 into 4, which is 4 modulo 5. So the remainder when 3 power 100 into 2 power 50 when divided by 5 is 4. Therefore 4 is the required remainder.